Okay, now we're going to talk about covalent bonding. This is another type of chemical bond that can be formed. We're pretty familiar now with the concept of electron transfer in an ionic bond, but that's not the only way that two atoms could join together. There's also something called covalent bonding, and it has to do with sharing electrons instead of transferring them from one atom to another. All right, and this term covalent, you should recognize at least this word valent and may think valent is sort of like valence, and that's right. So we're talking about the electrons that are in the valence level of atoms and how they could be shared to form a chemical bond. The first thing you really got to commit to remembering is that a covalent bond exists between two non-metal elements. Non-metal. So we don't see, with some exceptions, but we don't see metals in covalently bonded compounds, all right? So we're looking for elements that come from this neighborhood on the periodic table. And there's a lot fewer non-metals than there are metals, and so you just gotta remember which is a metal and which is a non-metal. Also take into consideration that hydrogen is a non-metal and it lives way over here on the periodic table, and it's often involved in covalent bonding as well as ionic bonding, so it's a little bit of a weirdo. So we're looking for compounds that are created from non-metals. Okay, and now that you know how to do Lewis dot diagrams, which just diagram the valence level of the electrons in an atom, you can use this to your advantage when you think about how electrons are going to be shared. Okay, and so when you look at like here's oxygen, for example, and when you look at this diagram, we see pairs of electrons and we see single electrons. Now, the pairs of electrons are pretty much out for this. Pairing up electrons is sort of what we're trying to do. And if these are already in a pair, they're not really open for business in the bond sharing or the electron sharing game. What you want to do is look for opportunities to link single electrons to each other, right? And so that then forms a pair of electrons that get shared between the hydrogen and the oxygen. And so this is a good situation for both atoms because they both get to feel like their valence level is full, even though it's not full all the time. If they're sharing the electrons, then oxygen feels like it's got an octet by sort of poaching one of hydrogen's electrons. And then hydrogen gets to feel like it's got a valence duet, which is its stable configuration, by just sort of sharing oxygen's lone electron. And so it's just a matter of sharing these single electrons between two atoms. Okay, and let's see how this can work with another compound. So here is oxygen, two oxygens and a carbon to make what we call carbon dioxide. This is probably a compound you're familiar with. So here, carbon typically sits in the middle of these structures here. And you'll notice that carbon has 4 single electrons. So it really wants to link those 4 single electrons up to any other single electrons in the area to form a bond. So the way that this happens is that maybe oxygen will share these electrons with carbon, and then maybe over here they share electrons in this way. And this makes what's called a carbon dioxide molecule. And we would sort of clean this up by putting these 2 lines on either side of carbon and the oxygen atoms here, and maybe put these pairs here because they didn't change. Okay, this is known as a double bond. Okay, the double bond results from sharing 2 pairs of electrons. Got it? So each of these lines represents 2 electrons. So this bond is actually made up of 4 electrons. 4 electrons spread over 2 bonds, here and here. Make sense? And I use the word molecule, and that's probably the first time that we're hearing that word here in chemistry. And the word molecule refers to these things that are covalently bonded. And it's a vocab term that gets, I think, misused quite a bit. You know, you don't have molecules if the atoms are ionically bonded to each other. You really only have molecules if we are covalently bonding our atoms together, okay? And here's one more, just to get the hang of this. Here's nitrogen gas. This is N2. And so nitrogen's Lewis dot diagram looks like this, where we've got our pair of electrons and then 3 singles. That's the 5 valence electrons in a nitrogen atom. And so what we want to do is link up these single electrons. And I've just sort of rotated where those electrons are to make this a little more clear. So here you can see that we're going to link our single electrons here, here, and here, okay, for a final overall molecule structure that looks like this. And that is known as a triple bond. Okay, and so these molecules can have either single, double, or triple covalent bonds. And in some of the more complicated structures, you might see, you know, a single bond between 2 atoms and then a double bond between another couple of atoms. It's all just about how the pairs of electrons can be shared between atoms, okay? And when we name these covalent compounds, we do this in a slightly different way than we're familiar with. Although you probably have heard a few of these. I've actually already used one of these terms already, and when I said carbon dioxide. And when we name these things, we use those prefixes like di, tri, tetra, and here they are. So mono is 1, di 2, that's where the carbon dioxide comes from. Tri is 3, tetra 4, penta 5, hexa 6, hepta 7, octa is 8, nona is 9, and deca is 10. And for sure, when we first start doing these molecular electron sharing sort of situations, we're probably going to be in the mono, di, tri, tetra, you know, range here. It gets a little bit goofy when you start, you know, incorporating a bunch of these other things. But let's just do some examples here and see how we're going to use these prefixes names. Okay, so first thing to know here is that when you see a chemical formula that involves all nonmetal elements, the subscripts that you see in the compound don't affect the name. I'm sorry, they do matter in the name. Bad brain fart. The subscripts are very important in covalent compound names. So for example, H2O, that 2 is really, really important here, and the 1 is important as well. Okay, so all we got to do is identify what subscripts are present, and remember that I just put a little 1 here by the oxygen. Even if there's not a subscript, just think of it as a 1, okay? And so we're going to use our prefixes to name this compound. So this is dihydrogen monoxide. And yeah, the prefix is really mono, but you know, it's just one of those little things, like if the prefix ends with an O and then the element starts with an O, you just use one O. So dihydrogen monoxide. All right, here's one, N2O3. All right, so the 2 is di and the 3 is tri. So we're just going to, you know, use our prefix di, which means 2 nitrogens, and tri, which means 3 oxygens. Dinitrogen trioxide. Okay, and here's another one, CCl4. So we really only have 1 chlorine and 1 carbon and 4 chlorines. Now, this is a special little rule here. If you only have 1 of your first element, you don't need to use mono. Okay, don't use mono if it's going to be applied to the first part of the compound. Okay, that's just one of those little quirky things. So you just call this carbon, and then we have 4 chlorines, so this is tetrachloride, okay? Carbon tetrachloride. Don't say monocarbon tetrachloride. People will know what you mean, but they'll probably laugh at you if you do it that way. And here's another example of that. This is a chemical that you've probably heard of this. This is called carbon monoxide, and it's a kind of a lethal gas if you breathe in too much of it. So we wouldn't say monocarbon monoxide. We would just call this carbon monoxide. Okay? So that's how the prefix system works, and that's how electrons get shared in molecular compounds, and hope that helps.